Chapter 9: Stress Transformation and Mohr Circle. So if you consider a cube like this and just consider a tensor of tension, so we do have sigma xx in x direction, sigma yy in y direction, and sigma zz in z direction. So they are the three normal stresses. And if you just go in the plane of x, which, for example, the each plane goes by the name of the normal of that. So the normal of this plane is x. So that's the plane of x. And this is a friction on that plane. So that goes by tau x. Again, this is tau x. And it just points toward the z direction. So the second component goes by z. So that's tau in the shear in the plane of x towards z direction. Likewise, this is shear in the plane of x toward y direction. Hmm? Likewise, with the same uh, analogy, you can just go by tau shear in the plane of y towards pointing towards the x direction. Shear in friction in y plane and towards the z. Likewise, you can say tau zx and tau zy. And the other interesting fact about the tensor of tensions are in they are mutually equal to each other. So tau xz is equal to tau zx, tau zy is equal to tau yz, and likewise tau xy is equal to tau yx. And if you just want to project them in the element, it just says if, for example, tau xy goes by 10 ksi, tau yx is exactly identical to the same, uh, the, is identical to xy, and they, for example, go with the same numeric value of 10 ksi. The other interesting fact about the uh, shear in tensor of tension, it just says they are either to a point, converging to a point, or diverging from a point. So they are converging to this point, they are diverging from the, for example, if you call this point A, point B, they are converging at point A and B, and they are diverging at point C and D. So it just says the shear stresses in tensor of tension, they are identical to each other, and at the same time they are either converging to a point like what you can see at point A, or diverging from a point, point C. Again, converging to a point and diverging from a point. Now we want to know what will happen if we want to travel from our old house of xy to our brand new house of, so this is our old house of xy. We want to travel to our brand new house of x prime and y prime by the angle of rotation of theta. And then we want to know what are the stresses on the new axis of x prime y prime after a rotation of theta, angle of theta. And that's a very frequent problem in engineering problems. So the all of a sudden element is changing, and we want to know what is the stresses in stress and strain also in different orientation. So let's see how to approach the problem. So it just says if we just take out an element out from the structure, and if we call this area delta A. Mhm. So that's delta A. There is a shear working on that area, and there is also a normal which is in x prime direction, as you can see here. And if this is theta, mhm, one can easily say if that's theta, this is theta too. And let's see the translation of just the plane. So if this is delta A, and this would be delta A sine of theta due to this angle, and the other area over here is nothing but delta A cosine of theta. Mhm. And again, there are forces like a normal force acting on delta A cosine of theta, shearing force acts on delta A cosine of theta, likewise a normal force acting on that, and a shearing force acting on delta A sine of theta. And now if we develop the equation of forces based on that element, you can and develop the equation of sigma fx prime, for example, goes 0. Mhm. So that's sigma x prime delta A. We need to go by all the forces which cancel out our uh, force of delta x, sigma x prime delta A. So we need to, for example, just consider the bottom side. So here, the area is delta A sine of theta, delta A sine of theta. And the forces are, for example, let's just go by a sigma tau xy, which is this one. And we just need this component of that force, which is tau xy delta A sine of theta times cosine of this angle, because we need this component of force. So if you write down the equation sigma x prime delta A minus tau xy, which is this component, delta A sine of theta, and then which component of that? That's a cosine of theta. That's a cosine of theta. And also we do need the sigma y delta A sine of theta, which is this force. Which component of that? Sine of theta. So that's a sigma y delta A sine of theta times sine of theta. That's the part for the bottom part. So that's again, we do need the forces which oppose the sigma x prime delta A in x prime. So we need a negative x prime. So that's a sigma tau xy delta A sine of theta, which is this force, and the component cosine of theta. So that's tau xy delta A sine of theta, the component of cosine of theta for that. And the other one is sigma y, which is the normal force, which applies on the plane of delta A sine of theta. And which component of that? The component of sine of theta, the red arrow. So that's minus sigma y delta A sine of theta times sine of theta. If we do the same approach for the sides, uh-huh, it gives us another set of equation, and if you add them up together, it gives you an equation of so that gives you, if you just go by the bottom and the sides and add them up together, it just gives you an equation based on sigma x prime, which is sigma x cosine squared theta plus sigma y sine squared theta plus 2 tau xy sine of theta times cosine of theta, which is sine of 2 theta. If you call that equation 1, mhm, and let's see what else do we have. That's from a trigonometry. We can have the relation between cosine of 2 theta is cosine squared minus sine squared. If you rearrange that equation based off sine of 2 theta, it just gives you sine squared is cosine squared of theta minus cosine of 2 theta. Mhm. And if you just rearrange that equation, and we do know sine squared plus cosine squared goes by 1. Mhm. So if you replace that, it just gives you 2 sine squared is 1 minus cosine of 2 theta, and that says sine squared theta, it's a half of in bracket 1 minus cosine of 2 theta. Likewise, with the same uh, approach, you can get the cosine squared, which is a half, the same equation, but this time plus cosine of 2 theta. Mhm. And if we call this equation 2 to 4, and if we add all those with each other, we get an equation for sigma x prime. Mhm. If we do the same for, if we do the same for sigma fy prime, here, and do the same approach for the forces, you can have an equation for tau x prime y prime, which is this equation. Mhm. At the same time, you can we do know sigma y prime. Mhm. Sigma y prime is obtained by replacing of theta in equation 1 by an angle of theta plus 90 degrees. What that means, it just says if we are in x axis and we have a rotation of theta, we reach to x prime. By another 90 degrees, we get to y prime because x and y and x prime y prime are perpendicular to each other. So that's a rotation of theta plus 90 degree from x to y prime. So if you just apply the same uh, uh, rule to sigma x prime, sigma y prime, you can easily get the equation for, and at the same time, we do know cosine of 2 theta plus 180 is a negative cosine of 2 theta. Sine of 2 theta plus 180 is a negative sine of 2 theta. If you add these two equation and apply the rule, you can get an equation for sigma y prime, which is a very similar to the equation 1, which we already had for sigma x prime. So if you consider sigma x prime and tau x prime y prime, they are a hint to an equation of a circle. Mhm. So that's equation of circle. Mhm. So, and the interesting part about that is in mid 19th century and early 20th century, and a German, uh, a brilliant German engineer called Christian Otto Mohr discovered the fact that if you just develop a circle which goes by his name, Mohr circle, as you can see here, it just gives you, it's completely compatible with the formula, and that's a nothing but a Mohr circle. So sigma x prime, sigma y prime, and tau x prime y prime are the comes from the equations. And if you just goes, and they are a representation of a circle which developed by a German civil engineer, Christian Otto Mohr, in 19 to early 20th centuries, and that's a discovery that you can, it makes the problems solving far easier than formula. Mhm. Mohr studied engineering at the Polytechnic Institute of Hanover in Germany in 1851, and that's a schematic of the current day Leibniz University at Hanover, Germany. And this is a more circle, and this is a late a photo of Christian Otto Mohr. So the stress transformation, working with the stress transformation with the use of this interesting circle is far easier. So it just says if we do have an element and we just rotate it by the angle of theta, and want to know what are the stresses and sigma x in x prime and y prime, we can easily by get the stresses by just drawing the more circle, rather going through the formula. You can solve it with one method and verify with the others, but I do recommend to work with the drawing of Mohr circle, which is makes the problem far simpler in terms of solution. Mhm. So just keep in mind if you are using the equations, uh-huh, just tau positive, it's a positive in y direction. So when using formula, mhm, a tau positive is defined to to be a positive direction at y direction. So this tau is definitely a positive. Mhm. And when you're using the Mohr circle, just look at the elements. So if, for example, the shearing force tends to rotate your element in a clockwise condition, so just go for a point at the top, uh-huh, above the axis, uh-huh. And if a friction or shear tends to rotate an element in counterclockwise, just put the point below x-axis. So that's the simple rules when you're applying the either formula and also plotting the Mohr circle. Hmm? We'll get to more problem solving in next videos, but that's a the concept part of this Mohr circle. Thank you.